Newton's understanding of gravity was adequate to allow humanity to travel from Earth to the Moon. Have you ever been perplexed by how quickly time goes by and wondered if our understanding of it is just the tip of a much larger temporal iceberg? At its essence, his insight is not merely a conjecture. It's a key that could unlock the mysteries of the universe, revealing a cosmos more intricate and awe-inspiring than we ever dared to imagine. How does Brian Cox's recent theory challenge our conventional view of time? And what potential consequences could it have for our comprehension of reality? As we investigate Brian Cox's groundbreaking theory about the nature of time in the vast universe around us, come along for an intriguing journey through the corridors of time itself. There are still enigmas to be solved, and some of them involve fascinating aspects of time and gravity, two essential aspects of our existence. Imagine a reality where time behaves peculiarly. It has the ability to speed up or slow down. Moreover, the force that keeps us grounded might not be as it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes an unusual turn. Albert Einstein, a distinguished figure, provided us with a fresh perspective on the cosmos through his theories of relativity. His work laid the foundation for understanding how time operates under various conditions, particularly when moving at extraordinarily high velocities. It all began in the early 20th century when Einstein proposed two revolutionary theories, both the general and the special theories of relativity. The special theory of relativity, introduced in 1905, transformed our understanding of time and space. In simple terms, it asserts that the principles of physics remain consistent for all observers who are not accelerating regardless of their motion. This theory introduces the concept of relativistic effects, including the well-known idea that time can dilate or slow down under specific conditions. One captivating thought experiment used to illustrate time dilation is the light clock. Imagine being inside a spacecraft moving incredibly fast, nearly at the speed of light. Within the spacecraft, a beam of light bounces between two mirrors that are perpendicular to the direction of movement. According to the laws of physics, the speed of light is constant for all observers, meaning the light beam must appear to traverse a longer diagonal path. The duration it takes for the light beam to cover its route should be identical for both the observer inside the spacecraft and the one outside. However, since the path is lengthier for the outside observer, it appears that it would require more time for the light to complete its journey. This perceived time discrepancy between the two observers is what Einstein termed time dilation. The moving observer experiences a slower rate of time than the stationary observer. In this scenario, time behaves differently based on your motion. Grasping how phenomena alter when they move rapidly, known as relativistic effects, is not merely a theoretical concept. Scientists utilize large machines, known as particle accelerators like the Large Hadron Collider, to propel particles at incredibly high speeds, nearly as fast as light. When entities move at such velocities, we must conceptualize time in a unique manner to make precise predictions and measurements. Albert Einstein formulated the special theory of relativity in 1905. And it revolutionized our perspective on the universe, particularly regarding time and movement. This theory challenges our instinctive notions. It posits that the laws of physics are consistent for everyone, even if they are stationary. This contrasts with our daily experiences, where we might believe that if something is already in motion and we add more speed, it accelerates further. However, Einstein's theory states that there is a maximum velocity that nothing can surpass, and that is the speed of light. In this way of thinking, events that appear to occur simultaneously for us might not seem that way for individuals moving nearly as fast as light. Another idea emerging from this distinctive viewpoint is length contraction. This implies that if an object is in motion, it appears shorter in the direction of its movement when observed from a stationary location. Then there's the renowned equation E area mc2, which illustrates that energy and mass can convert into one another. This is significant for comprehending how minute particles behave when they are moving at high speeds, as well as for phenomena like nuclear reactions when atoms split. In reality, special relativity is not just an elaborate theory. It plays a role in everyday technologies like GPS. When GPS satellites transmit signals to your device, they are in motion, and because of this movement, time behaves somewhat differently for them. If we failed to consider this time dilation effect in our GPS computations, your navigation could be significantly inaccurate. Thus, special relativity informs us that time is not uniform for everything and everywhere. It is contingent upon how entities are moving. This notion challenges our typical perceptions of time and space. It's like saying that our usual understanding of the universe might be a little off. According to the special theory of relativity, time is not static. It is affected by motion. Certain fundamental concepts, such as the speed of light remaining constant and the interrelation of energy and mass, have been confirmed by countless experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deeply into the connection between gravity and the structure of the universe. It challenges the outdated notion that gravity is merely a force that pulls objects from a distance. Instead, it indicates that gravity arises because space and time are warped or bent. It's akin to saying, hey, gravity isn't an enigmatic force. It's just how things naturally behave in the universe. According to Brian's interpretation, general relativity necessitates viewing the universe as a four-dimensional entity, merging three spatial dimensions with one of time. Space and time are shaped around large objects like stars, planets, and even humans within this framework. This shaping is what we perceive as gravity. Think of space-time as a huge, pliable blanket. When a heavy object like Earth is placed on it, it creates an indentation. If you position something smaller, like a ball, near Earth, it will roll toward this depression. This reflects how things react to space-time curvature rather than a mysterious force like gravity. General relativity offers a robust explanation for how celestial bodies navigate in our solar system, such as planets orbiting the Sun. It can precisely predict the trajectories of these planets, including how Earth follows an elliptical path around the Sun. According to Brian, this differs from the outdated concept of gravity merely pulling objects together, which struggles to elucidate how planets move as they do. The new idea is that time and space are curved like a flexible fabric, more in line with what we see. A crucial event that validated the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a scientific expedition to observe how light from distant stars bent as it passed near the Sun. According to Einstein's theory, the Sun's mass would cause the starlight to curve slightly. During the eclipse, when the Sun's brightness was temporarily obscured, the team observed that the light did indeed bend, just as general relativity predicted, thus confirming the theory's credibility. Just as motion affects our experience of time in special relativity, gravity also alters time in general relativity. In areas where gravitational forces are extremely intense, such as near massive celestial objects, time actually moves more slowly compared to regions with weaker gravity. For instance, if you were near a black hole, your clock would tick slower than a clock far away from that immense mass. General relativity also introduced the concept of black holes, regions where gravity is so strong that not even light can escape. The boundary surrounding a black hole is called the event horizon, beyond which nothing can return. Once something crosses this boundary, it's pulled inexorably into the black hole. Einstein's theory of general relativity also had implications for our understanding of the universe's shape and behavior. Initially, Einstein added a cosmological constant to his equations, believing the universe was static. But after the discovery that the universe is expanding, he called this addition his greatest blunder. Ironically, the idea of an expanding universe became a fundamental piece of the Big Bang theory, which describes the universe's origin and growth. Another major outcome of general relativity is the prediction of gravitational waves, ripples in the fabric of space-time caused by extremely massive objects moving rapidly, such as merging black holes or neutron stars. These waves were directly detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, offering further proof for Einstein's work. General relativity has been tested in a plethora of experiments over the course of time, and every single one of them has demonstrated its accuracy, whether it was through the detection of gravitational waves, the motion of planets, or light, bending in close proximity to massive objects. Physics thrives on exploration and challenge, even though the idea that gravity might be misunderstood can be surprising, given that we experience it every day. Existing concepts. Scientists like Brian Cox critically examine established theories. One alternative concept is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at extremely low accelerations, particularly in galaxies, potentially explaining their behavior without invoking dark matter. MOND proposes that under these conditions, gravity strengthens rather than introducing invisible matter. Debates around gravity also touch on mysterious phenomena like dark matter and dark energy. Despite the widespread acceptance that these are required to explain a variety of observations, some scientists argue that they are unnecessary and offer alternative theories in their place, some involving new forces or unknown particles. In science, novel ideas are not simply dismissed. They go through a stringent validation process. For instance, Einstein's idea of time as a fourth dimension, integrated into the concept of space-time, opened discussions about time travel, wormholes, and other theoretical possibilities. According to the laws of physics, it is unlikely to be possible to travel back in time, as suggested by Stephen Hawking's chronology protection conjecture. Still, ongoing experiments and observations aim to find out whether these new ideas can provide a more complete understanding of gravity. Despite numerous new theories, none have yet surpassed general relativity. It remains the best supported and most accurate framework for explaining gravity, successfully accounting for planetary motion, the bending of light, and much more. General relativity remains strong because it's elegant and broadly applicable. Einstein's theory of special relativity also holds that the speed at which you move has an impact on how time behaves. Space travel places a special emphasis on this. Space exploration is thrilling, but also immensely difficult. The cosmos is vast, and according to Einstein, nothing can exceed the speed of light. This imposes a major barrier to traveling between stars, even the closest ones, because of the enormous time required to reach them. To understand time during space travel, consider the famous twin paradox. Imagine two twins. One stays on Earth, while the other travels to a distant star at high speed and then returns. Upon returning, the traveling twin finds that less time has passed for them than for their sibling who remained on Earth. This means the traveler has effectively moved into the future, time dilation, where time slows down for those moving close to the speed of light, is a real effect confirmed by both theory and experiment. Time is crucial for astronauts. The longer a space mission lasts, especially if near light speed, the more time slows for them. So, while they may only experience a few years, many more could have passed on Earth. This impacts not only biology and psychology, but also the functioning of equipment. Technology on spacecraft must be designed to account for these relativistic effects to function accurately. Back on Earth, we witness these effects daily through GPS. These satellites move fast and exist in weaker gravitational fields compared to Earth's surface. Their onboard clocks, therefore, operate slightly differently. Engineers must account for both types of time dilation due to motion and gravity. GPS accuracy would suffer greatly otherwise. Now, let's examine why time flows in only one direction. Time governs our lives, flowing from past to present and into the future. But why does time seem to move forward and not backward? The answer lies in entropy, a measure of disorder or randomness in a system. The arrow of time is linked to the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time. It must either increase or remain the same. In simple terms, things naturally become more disordered over time. Imagine a deck of cards neatly arranged. If you shuffle it, it becomes random and disorganized. That shift from order to disorder is a clear example of time moving in one direction. Everyday events, like melting ice or coffee stirring, also show how time causes things to become more chaotic. This tendency toward disorder, toward increasing entropy, is what gives time its one-way direction. It's not that the laws of physics prevent time from moving backward. In fact, most physical laws are time-symmetric, meaning they work the same whether time runs forward or in reverse. However, because entropy increases in the direction we experience as forward, time feels like it flows from the past into the future. In our everyday experiences, we rarely see events unfold in reverse. Ice doesn't spontaneously reassemble into cubes, and spilled coffee doesn't leap back into the cup. These examples illustrate the irreversible nature of most real-world processes due to the second law of thermodynamics. The arrow of time is inextricably linked to this increasing entropy, a concept physicists use to describe the direction in which time progresses on a cosmic scale. This idea has enormous implications. The universe began in an extremely ordered state with very low entropy, a smooth, dense configuration known as the Big Bang. The universe gets more and more chaotic as it grows. Matter disperses, galaxies form, and stars explode. This evolution from order to disorder defines the direction of time itself. Some physicists speculate that if entropy defines time's arrow, then in a hypothetical scenario where entropy began to decrease, time might feel as if it were moving backward. But as far as we can tell, entropy has only ever increased in our observable universe, meaning time has only ever flowed one way from past to future. This discussion leads us to profound, philosophical and scientific questions. Is time a fundamental aspect of reality, or is it an emergent property that arises from entropy and thermodynamics? Is it possible that our perception of change in memory creates an illusion of time passing? These are questions that thinkers like Brian Cox and other contemporary physicists continue to explore. Furthermore, some modern theories in physics, particularly those arising from quantum mechanics and attempts to unify it with gravity, suggest that our traditional understanding of time may be incomplete. In certain quantum theories of gravity, time may not even exist as a fundamental property. Instead, it may emerge from deeper, more abstract structures in the fabric of reality. Despite these speculative frontiers, our current best models, special and general relativity, offer us a powerful framework to understand time's behavior on both cosmic and human scales. They explain why time slows down near massive objects or at high speeds, why GPS needs to correct for time dilation, and why we observe the universe evolving toward increasing disorder. As our technology and scientific methods improve, we continue to refine our understanding of time, gravity, and the nature of the universe. We are constantly testing the limits of what we know about time through high-speed spaceflight, gravitational waves, or black holes. Ultimately, time is more than just what we track on a clock. It's a dynamic, complex phenomenon that we are only beginning to truly understand. We are getting closer to answering some of the most profound questions that humanity has ever asked as we look deeper into the cosmos and as physicists like Brian Cox push the boundaries of theoretical knowledge. What is time? Why does it move forward? And what does that reveal about our place in the universe?